History of parallel postulate.
Alright, so we're diving deep into the parallel postulate. This is one of the most debated ideas in geometry, right? Euclid's fifth postulate, what makes it so significant to the entire structure of Euclidean geometry?
Absolutely. The parallel postulate is unique among Euclid's five postulates. The other four feel kind of intuitive, but this fifth one about parallel lines just isn't as self-evident. Euclid stated it as if a line segment intersects two straight lines and makes the interior angles on the same sides less than two right angles. Those two lines, if extended indefinitely, meet on that side where the angles are less than two right angles. It feels more complex.
Right, and I read somewhere that for centuries, mathematicians tried to prove it using only the other four postulates. Why do you think that was such a big deal?
I think they wanted to streamline Euclidean geometry, almost as if to make it simpler. If the parallel postulate could be proved using the other postulates, geometry could rely entirely on more intuitive concepts. Plus, there was this belief that the fifth postulate seemed less universal than the others.
And by less universal, I guess you mean that it felt dependent on specific spatial assumptions rather than general fundamental principles. It seems like many mathematicians weren't satisfied until they either proved it or developed alternatives.
Exactly. Proclus, for instance, thought that postulate was something that should be derivable from the other axioms, so he and others searched for ways around it, which is why the postulate's role in Euclidean geometry is so crucial. It shapes our understanding of congruence, similarity, and of course, parallelism itself.
It's fascinating how much hinges on that single postulate. I mean, without it, the Euclidean geometry just isn't the same.
Agreed. Now let's think about whether Euclidean geometry could function without it. This is where the necessity of the parallel postulates gets questioned. I read about Saccheri and his attempts to prove it. He started by assuming it was false, so that instead of having one parallel in line though a point not on a given line, there were either no parallels or more than one.
That's right. Saccheri even came up with his own type of quadrilateral, the Saccheri quadrilateral, but his logic led him to strange conclusions, which he eventually dismissed as absurd. Since he was working under Euclidean assumptions, it was like he almost stumbled onto hyperbolic geometry without really realizing it.
Yes, that's a great point. Zachary thought that he was proving the absurdity of alternative geometries, but this work inadvertently contributed to non-Euclidean geometry. It's almost ironic.
And yet, for Euclidean geometry, the parallel postulate still holds as an essential component. But what if we go a step further and ask, is the parallel postulate even necessary for geometry? What do you think?
That's a really challenging question. I'd say it depends on the type of geometry we're talking about. For Euclidean geometry, yes, it's necessary. But as we see with non-Euclidean geometries like hyperbolic and elliptic, geometry can exist without it.
True. It's fascinating how non-Euclidean geometries emerge from this question. In hyperbolic geometry, for example, there are infinitely many parallel lines that can pass through a given point, while in elliptic geometry, there are no parallel lines at all.
Right, and each geometry remains internally consistent its own world, so to speak. In fact, some of the alternative geometries built on the negation of the parallel postulate have real world applications like in physics, where they're used to describe the structures of space time.
That's mind blowing. The universe itself may not be purely Euclidean. I think that's why the question of whether the parallel postulate is necessary has such philosophical implications. It challenges our assumptions about space and even reality.
Definitely, and it brings up another interesting idea statements that are equivalent to the parallel postulate. Clairaut and others work on restating the parallel postulate in different ways. Have you looked into some of these?
Yes, Clairaut's version was like a simplification, right? He said that through a given point, only one line can be drawn that never meets a given line. It's pretty straightforward and has the same implications as the original parallel postulate.
It does, and Clairaut's phrasing made the postulate easier to digest conceptually. But there's also Zachary quadrilateral approach, where he assumed that a quadrilateral with two right angles could be used to simplify the two parallel postulates.
Yeah, Saccheri quadrilaterals becomes a powerful tool. He assumed that if you start with a quadrilateral with two right angles and try to make a consistent geometry, you end up with either Euclidean or hyperbolic conclusions, depending on how the angles add up. It's like creating a test structure for parallelism.
Right, and each of these approaches, when assumed to be true, implies that parallel postulate in some way. It's fascinating because it's like discovering logical shortcuts that all lead back to this one central idea.
Which makes me wonder, if these equivalent statements imply the parallel postulate, could we theoretically swap them out in Euclidean geometry and still get the same results?
In theory, yes, the geometry would still work, but it would feel different. It's like switching recipes to get the same end product. Each recipe involves different steps or flavors but reaches the same outcome. This flexibility hints at why there are multiple ways to interpret and apply the postulates.
Well said. I guess that also explains why mathematicians were constantly trying to rephrase or simplify the postulate. The equivalences allow for versatility in applications and teaching approaches too.
Definitely. Speaking of teaching, I wonder how we could convey the parallel postulates' impact to students who might find it abstract. Would it help to discuss real life analogies or historical context?
That's a great idea. We could, for instance, talk about how Saccheri or Clairaut struggled to prove something that seemed self-evident but was actually elusive. This historical perspective might make it relatable and show how the parallel postulate connects to the human desire for logical certainty.
Or we could use spatial analogies, like in architecture or city planning, where parallel lines play a vital role. Imagining what would happen if two streets designed to be parallel suddenly intersected could make the concept more tangible.
Yes, and by illustrating non-Euclidean geometries like hyperbolic and elliptic as an alternative worlds, we could show that different assumptions lead to different but valid outcomes. Maybe that would make the parallel postulate uniqueness more understandable.
Exactly, because it emphasizes that while the postulate feels necessary for Euclidean geometry, it's not universal. It's like a rule specific to particular type of geometry which broadens students' perspectives.
That's what I love about this topic. The parallel postulate is just one assumption that leads to a whole universe of geometrical rules and truth. Understanding its implications, alternatives, and equivalence is like gaining insight into the very nature of mathematical thinking.
Well put, and ultimately, discussing the parallel postulate's history and its implications can help students appreciate the value of questioning assumptions. It teaches us that challenging a seemingly basic rule can open doors to entirely new fields.
That's the core lesson, isn't it? The pursuit of understanding the parallel postulate's necessity and role has reshaped geometry. It's like a testament to the power of questioning even the most fundamental ideas.
Absolutely. Through the parallel postulate, we see that geometry is not just about shapes and lines. It's about concepts, logic, and exploring possibilities. It's exciting to think that something as simple as line and a point not meeting can be so profound.